Yeah, as I was saying, the main idea, so I'm just is uh, the relationship. Yeah, the divergence theorem governs the relationship between what I'm calling here internal um, integral and boundary integral. Yeah. So specific to this divergence theorem, when it comes to this divergence theorem is for three-dimensional problems. Yeah, when you have the internal as the volume integral and the boundary is the surface integral. So this is the gist of the divergence theorem that I want everybody to see this. This is the big picture view, yeah, of this mathematical relationship. And from here, you would know that. Okay, so let's just pick up the statement of the divergence theorem. Let me switch to this. I'm going to grab the statement here. Um, okay, if I, all right. So if I put it in this standard form here, then it would be the other way around, yeah, for the statement at the top here. So this would be the volume integral, and the left hand side is the surface integral. Yeah. So what is the implications here? Uh, in certain problems or application, it is easier to deal with volume integration. Yeah, and so that means to evaluate the surface integration, if the problem is easier with volume integration, then you would do volume integral. Yeah, some problems, it may be easier to find the value of for the surface integration. So if you want to, if your final objective is to find certain quantities that involve the volume integral, but it turns out that mathematically it's easier to work out the surface integration, then you would do surface integration. So that's the for me the beauty of this relationship. Yeah, it relates surface, which is 2D, to the volume, which is 3D, right? 3D geometrical stuff. And so with this kind of concept, you can this where in the book or in the videos, I list out or sort of like arrange the applications with this divergence theorem. As you can see from the book, so from this divergence theorem, so let me just, don't know if I don't think I have it in here. Low, okay. This is the application in electrical engineering. Yeah, this one. Okay. I think I'm just going to capture this again. Okay, let's look at this, the list here. Yeah, I expect you to know from the book and from the videos, these three. Yeah. The first two, which is for like physics of electricity and magnetism, yeah, for the purpose of this semester, you don't have to really learn that. Yeah, we just focus on this last three. So I expect you to be able to understand how the for all these three here, Archimedes, heat, and quantification, how they are being derived. And for this Archimedes principle, which is this is basically in the field of what we call hydrodynamics. If you are in now I try to recall the term. It's not really naval engineering, but let me check this. Me find first. Marine people who are involved in shipbuilding. Yeah, so in marine engineering, marine. This is like a big part of the study, right? Because it deals with whether your water transport can float or not. Yeah. Of course, if you build like a submarine, we want to make sure that it can be under the sea, and or you build a ship, it will float. So this one of the way is looking at this from this so-called hydrodynamics principle or Archimedes principle. I would say that if you look at all, in fact, 5 of these applications, it's about conservation, we can apply the divergence theorem here uh, because of conservation, I would say laws. Yeah, there's remember there's an S here because like in continuity equation, we are talking about conservation of mass. Yeah, and for heat equation, it's conservation of energy. And for Archimedes principle, this is basically, I would um, think about this as it's just a balance of force, yeah, balance of forces. So balancing and conservation, it's very much related, yeah. And just to give you what you should expect in terms of what I usually ask in tests or exams. For example, in Archimedes principle, this happens again, so I have to restart. Okay. Give me a second here. So see, I lost some of the notes I put it earlier, but you got the idea. The main thing here today is for you to get the idea of this conservation principle and how it applies to the divergence theorem when we want to model um, these phenomena in physics. Yeah. Um, so just now I was saying the kind of question that I usually ask. So let's look at this. I want to focus first on this Archimedes principle here. Yeah, if you uh, this is bad. If you okay, I want to open the practice problems. Give me a second here. Oh, while doing this, I can quit this and you can see my problem set, right? Okay, thanks, Muhammad. Um, so I'm going to this section 7 in the divergence theorem. If you look at this example in question 3, I have this is I think it appeared in an exam several years ago. Yeah, this is a kind of problems that I usually ask in the divergence theorem. So let me reopen uh, my OneNote again. I don't know why today it's frequent, this problem. Share content. So now I'm on OneNote again. If just now the kind of problem that you see. For example, I would ask, um, okay, first of all, when it comes to hydrodynamics, it's always about a solid object in liquid, in this case in water. Yeah. And these solid objects can either be, if this is like a water level. So I'm gonna create like a very long. So we have this atmosphere, and this is water. So, for example, here I can have like a cylinder, right? Usually, I because of the calculation and the hand calculation, we only restrict to simple shapes. Yeah. So my common shapes is of course cylinder horizontally. I can also have cylinder in this way, but of course, if you have this, the calculation for the integral is very simple, right? This one you have to think more how to set up the integral. And I also have um, a sphere. As you can see, a sphere, of course, it can float in any way, right? So it can have, let me just put it into some thing here to make it like a like a sphere shape. So if it floats like this, you're gonna have to set the integration in one way, and if it floats like this, where most of the solid is in the water, it gonna have different way to set up the integration. So you have to be aware of all this. What else? What other shapes? Yeah. I also have sometimes a cone. This is a cone. Um, it floats like this, and it can also be. I don't know. Which does anyone know which one is inverted cone and which one is an upright cone? It depends on uh, how this mathematician define. Let me just grab this part here and draw again. You can have a cone like this. Let me see. Cone. I don't. Okay. So yeah, this is what we call inverted, right? And you can see here, if I were to find either the surface integral of this part here or surface integral of the part in the water here, the setup of the integration is different, right? So this is the thing that um, um, yeah, you have to be aware. So what else? So I'm extending the water line further. Um, Okay, in my let's say good mood, I would give you like a very simple like a box problem here, right? But it's very rare because the integration is not very exciting here, right? I can also give you it's the same like in the practice problem. Um, a tetrahedron, yeah. So this can be quite complicated. I haven't asked this kind of um, problem um, in test or exam. Yeah, but it can be done, except that takes a bit more deeper thinking how to set up the whether you have to do a surface integral or volume integral, and if you want to do either integral, how do you set up the limits of integration? Um, what else? What other shapes? I think these are the common geometries that I usually ask in hydrodynamics problem. Um, there is, of course, so this is the thing about mathematics. You can invent more complicated problem, but I never managed to discuss this with you, so I never include it. For example, for example, it can be done. It can be done in solving it. What if you have a solid? Let's say this solid is a cylinder, and the weight distribution of the cylinder is not uniform. So you can distribute the weight such that it's tilted when it floats. Now things get very interesting. how do you how do you um, um, solve this kind of problem? Um, so this is a big question mark here. This would be nice to have as an open problem, like a project for you to work, but not this semester. So we can sort of like ignore this. I don't know. Maybe I will put this as like an open problem in a test. Maybe I don't know. But if I put this kind of problem, it's not like I ask you to solve. Yeah? I probably ask you to like give ideas, yeah, your ideas how to find a solution. Okay, so this is the kind of problems that I usually ask in Archimedes or hydrodynamics principle. Uh, I didn't mention here, but the main point here is to look for this what we call um, buoyancy. Yeah? I never remember how to uh, buoyancy or Buoyancy. Okay, basically, this is what we are interested to solve for. Yeah, because this buoyancy, or so we call this net force, is the one that keep the solid objects floating at a certain level. Yeah. Okay. What else? Anything you want to ask about Archimedes' principle on hydrodynamics? It's all in the videos and in the book. Um, when it comes to the other two, this heat equation and continuity equation, so these two is mainly I expect you to know how the derivation is. Yeah, how to derive. As you can see in my practice problem here, there's a question 2 is about derivation of this divergence theorem. Okay, this is what I expect. How to derive, and of course the principles. Yeah, principles and meaning of this principles and meaning of these two equations. It's not like this is something unique. These two equations appear in your other courses too. Maybe not heat equation. Heat equation you will come across later on, either in third or fourth year. Um, but continuity equation, this is basically the foundation in your fluid dynamics and fluid mechanics. So I expect you to understand the derivation and the principles and the meaning of these equations. Yeah, this question by Xing Han. For the practice problem, any answer? I don't know. Are you referring to a specific question or for any problems here? The some of the problems for example, for this question number 3, I already include the answer here. Some of these there is no answer, but what I expect is you to you can verify the answer, and also you can ask me for to verify the answer. Okay. Yep. All right. Okay. So you're all clear about this divergence theorem. As I mentioned, the principle is in this the idea of relating the surface, and yeah, I also wants to mention boundary. Yeah, that. So these are the keywords here, right? It's internal, that relates to the so for 3D it relates to the volume, and the boundary in 3D relates to surface, right? These are the key principles of Divergence theorem, and then you have conservation. This is another um, key idea for the application of divergence theorem. Okay. Um, what else? So I'm switching to my slide just to see whether I missed out on something. Okay. These are all the derivations. It's in the video. This is modeling. Okay, fine. That's the main thing that I want to give you overview about this divergence theorem. One last thing is something that you want to be careful in terms of understanding this here. Wait. I think I will just I sort of so if you look at the book, maybe I just directly share the book. It's easier because you are learning from my book anyway. Let me where is the book? There is the book. Okay, let me go through the page here. Yeah, the divergence theorem starts at 3.9. What you should do is, as I mentioned, I expect you to be, because divergence theorem involves volume integration and surface integration, I expect you to know how to do these two kinds of integration. So for that reason, I have like the previous sections here, for example, section 3.8 and even 3. Yeah, section 3.8. And in fact, before these two, this is more like a review so that you know how to set up the surface integral, and then also with volume integral. Volume integral, it's not that difficult for this problem. It's more, I would say it's more difficult usually to set up a volume integration, sorry, surface integration. So I've made like a review in here. So let me, so coming back to 3.9, the divergence theorem, I have the derivation here and start with this electromagnetism. For hydrodynamics, where is it? Did I miss it somewhere? Continuity equation. This is heat equation. Yeah, this so this is also the one thing that I want to emphasize. So I want to get this. Okay, let me just paste it here and rearrange this. Okay. Um, uh, you can see. I hope you can see. This is the standard form. This is the standard divergence theorem, and you can see that this is this operator. This is the divergence. Yeah, this is why we call this divergence theorem. As you can see in here, within this triple integral, this is gradient. Yeah, and this P is a scalar quantity, while U here in the standard divergence theorem, this is a vector quantity. But it can be, it's this is a, some people call it's like a gradient theorem. Um, but it's something that you should see the difference here. Yeah, the top equation here is being derived by this divergence theorem because a scalar is just one component of the vector, right? But it can be proven. Yeah, this relationship is true. So, and this is the form that you use in the hydrodynamics. Hydrodynamics. Okay, this is what I want you to be aware of. Um, I want to repeat this. I mentioned this many times. If you want to send message, do it in the public chat box. So the question was the submission of the code. You are aware the code only accepts one .m file. Yeah, it doesn't accept a zip file, PDF file, multiple files. It only accept one, and then it must be in a .m file. As I explained in the assignment, you work your code in your main file. That will be your .m file where you call the other file. The other file is something that you download and you don't change it, right? So it's not your work. So you just submit your own file, which is the one that you work on. Okay, any more questions?
Hi, hi, doctor. I have a question.
Yeah, Mahesh. Right.
The code, if not me and my friend was trying to do the code, and we managed to get the answer, but the way to get the answer is we had to even change the NME simplex code. There was an error in the original code that we had to add the semicolon in some places.
I see. Okay.
Because if we copy from the web page, we get, if not mistaken, the x6 equals to 1. And if you get that, the minimum cost will be around seven something like that. But if we change the code in the NMA simplex, we manage to get a lower number, which is it's better because it's a minimal cost.
Okay. I didn't expect it. I was expecting you should not, or you don't need to change anything because it's supposed to be, I assume it's supposed to be correct, but it seems, since you said there is a bug, and also Wai Ching here saying there's a bug, I will change the submission link so you can upload the two MATLAB, right? Two MATLAB files. So so then if you change the original simplex, the what is it called here again? It's NMA simplex.m. If you change it, then you upload it. I will set the link later. Okay.
Okay, noted, doctor. Thank you.
All right. So any more questions about the Bayes theorem or about your assignment or anything else? Almost time here. So no more question. All right. Okay. Thank you. I'll see you in 2 weeks, right? Next week. Oh no, it's only Wednesday. So I'll see you on Friday. Eh? Thank you and bye bye and assalamualaikum.
Wait, doctor, what do you mean by Friday?
Oops, cancel. Don't we have class on Friday?
They changed it to Thursday.
Uh, was that from the announcement by Dr. Siti Sarah?
The announcement was from Dr. Sarah Kamal.
I was okay. Didn't read it. I
In the
was
Telegram groups.
assuming this is for the after the mid-sem break
Yeah,
because
after mid-sem break.
yeah, but yeah, this is after mid-sem break. But with me, you still have one more, right? One more class this week. Um,
Oh, yes, doctor. Sorry, I thought you meant after sem break. That's
no,
why.
no, I mean this week.
And then if this week, then Friday still got class.
Okay. So today is the 18th, and Friday we don't. This Friday, this coming Friday, the 20th, we don't have any um holiday. So class is as usual. Yeah. And then after that, you will go to your mid-sem break for 1 week. Then when you come back, you will have with Dr. Sarah, which she already set the new timetable, and then of course there is this one test with me. Okay, then see you this Friday. Friday we'll just I'm just going to wrap up this whole thing, and then together with the modeling, this a short discussion of modeling. Okay, bye.